Today we are continuing with area on the larger series on measurement. So far we've covered length, perimeter, circumference, and have begun exploring area. In today's video we'll look at the features of circles, sectors, and ellipses. We'll look at deriving the formula for area of a circle, and we'll find the area of circles, sectors, and ellipses. You might recall from the video on circumference of a circle and perimeter of a sector that a circle has diameter, highlighted in green here. It has a radius, which is half of the diameter, highlighted in yellow, and the circumference, which is the outside of the circle, which is highlighted in red. A sector is a section of a circle split by two radii. Half a circle has a special name called a semicircle. A quarter of a circle also has a special name named a quadrant. An ellipse looks like a squash circle. Has axes A and B. You notice that where A equals B, the ellipse is going to become a circle. Discovered in the circumference of a circle and perimeter of a sector video that circumference is calculated by 2 pi r, where pi is a mathematical constant that links a circle's diameter to its circumference. If you'd like more information on pi or the circumference of a circle, please have a look at that video. Imagine a circle is cut into small sectors and arranged as shown here. If you continued to cut the circle radially into even smaller wedges and join them together to approximate a parallelogram, eventually the rearranged shape would turn into a rectangle. You notice the bottom parallelogram here is half the circumference. Therefore, we label it pi r, because the circumference of a circle is 2 pi r. And if we've got half of the circumference, that's pi r. The perpendicular height is labelled r to represent the radius of the circle. As the circle is cut into more and more pieces and rearranged, the parallelogram turns into a rectangle. Its area, the area will be given by the length times the width, which is the formula for the area of a rectangle. Now we can substitute in our values here, and we can substitute in pi r, and we get the formula for the area of a circle, which is pi r squared. Here I'm going to attempt to simplify an explanation of the link between the radius of a circle and its area using a mathematical technique known as limits, which is beyond the scope of this video. This technique was used by Archimedes over 2,200 years ago. You'll notice here that the inside of a circle can be broken down into a number of congruent triangles along its diameter or radius. The area of the circle can then be approximated by adding up the area of all of the triangles. So in our top circle there, we've broken it up into 6 triangles, and we're going to approximate the area of the circle by adding up the area of the 6 triangles. And the area of a triangle is given by half base times height. You'll notice, however, that there will be some error, and I've highlighted this in red around the outside of the triangle. As we break the circle down into more triangles, you'll notice that the error reduces. I've highlighted this in the bottom circle where we've broken it down into far more triangles. And we can represent that by, so if we're going to break it down to more and more triangles, we can substitute 6 with n, which is the number of triangles. And you'll notice that the base of the triangles becomes the circumference of the circles as the number of triangles increases. So I've just rearranged the formula here. And what we do is we say that as n goes to infinity, which is the number of triangles, the limit of n times b becomes the circumference of the circle, which is 2 pi r. So I'll let you think about that a little bit more. And again, we'll say as n goes to infinity, which is the number of triangles, h, which is the height of the triangles, the limit of the h will be r, which is the radius of the circle. I'll let you think about that a bit further. So we say the area of a circle is given by the half 2 pi r times r. And then that's simplified to pi r squared, which is the area for a circle. Let's look at finding the area of a circle. So we know from the previous 2 slides, a circle's area is given by pi r squared, where r is the radius of the circle. Let's have a look at an example. We're given a circle with a radius 6 centimeters. We write our formula. substitute in our value, and we evaluate. So the exact answer for the area of this circle is going to be pi 36. And our answer, correct to 2 decimal points, is going to be 113.10 centimeters squared. A good way, some people get confused between the formula for the area of a circle and the circumference of a circle. A good way to remember it is the area of a circle has a square in it. So we've got pi r squared, and the units for area are given in squared, in this case 113.10 centimeters squared. The circumference of a circle doesn't have any squares in it because we're measuring length, and so are the units. It's a good way to remember it. Let's find the area of a sector. Remember that a sector is formed by dividing a circle with 2 radii. The angle between the 2 radii determines the size of the sector. If we use the angle to calculate the fraction of the area of the circle. So we can use, in this case, theta over 360 times pi r squared. So let's look at an example. In this example, we've got a circle. It's been broken down, and it's 270 degrees of an entire circle. So we rewrite the formula with 270 on 360 times pi 3 squared. And here we have our exact answer. So that can't be simplified any further without rounding. And then we solve it, and we get 21.21 meters squared, which is rounded to 2 decimal places. Let's look at the area of an ellipse, which is given by pi AB, similar to the area of a circle, except we don't have a radius here. We've got A and B, where A and B, in this case, they're referred to as the semi-axes. We've got the example. We've got the formula. We substitute in our values. We've got A and B, which are 5 and 2 respectively, and we evaluate. That's the exact answer. And then we get the final answer rounded to 2 decimal places, 31.42 meters squared. And that's it for today's video. In the coming up videos, we're going to look at the area of composite shapes and the area of irregular shapes. And then we'll start on volume and capacity. Thank you.